So the problem today is find if path exists in graph, which I think is the most approachable graph problem. Graph problems are usually pretty hard. This one's pretty easy. There's a bidirectional graph with m nodes. We're given edges where edges at I contains the number of two nodes that are then denoted as being connected. So edges has 0 and 1, and then those are connected. Find out if there's a valid path. So here we can see everything's connected. It doesn't matter what source and destination are. There will always be a valid path. Here we can see 0 and 5 are source and destination. Those are not connected because there's no path. I think this problem is a good one because there's multiple comparable ways to solve it. And the comparison to me is actually pretty interesting here. So stick around if you want to look at that. But I'll just start out with a simple breadth first search. That's probably the most straightforward way to do this, and it works well. So the first thing we want to do is create an adjacency list. We say that. So we're saying adjacency is a new list for, we could just say I, but this is kind of fancy, for I in range n. If we just said this times n, I see people often asking, why can't you just do this? Or what happens if you do this? The problem is this is creating a new list, yes, but then it's just filling ADJ with n pointers to that same list. So if we can imagine this big 2D list that's supposedly being created, anytime you change anything in any column, it changes it in all the other rows on that column. So we have to say this. Anyway, this denotes ADJ at I represents the ith node, and it represents all the connections that the ith node has. That's different than this format edges that we're given, because edges is just seemingly an unordered list of all of the edges, which maybe there's a use for that, but it makes it hard to do things like depth first searches or breadth first searches. By the way, you could do a depth first search for this too, but I think breadth first searches have a more reliable time complexity, I would think, and in my mind are a little bit more, they make more sense conceptually. So then we fill up ADJ, we say for u, v in edges, ADJ at u dot append v, and then ADJ at v dot append u. So then that's filled up. If this wasn't bidirectional, we just would delete this line, but it is bidirectional, so. And then we just perform a breadth first search starting at the source node and then building out in these concentric circles until we either find the destination node or we exhaust all of the nodes. So we immediately know that, well, we're going to use a queue, and then I'll fill it with the source node. And we're also going to use scene, which is a set, just to check to make sure we don't like go from 0 to 1 and then add 0 again and then add 1 again or any of that, just to keep track of what we've already covered. And we immediately know we're going to have something like while q, and then if this ever runs out and we haven't returned anything, then just return false at the end. You can say false or 0 in Python, they equate to the same thing. So while q, let's just say, let's keep the same syntax, u equals q dot pop for v in ADJ at u. If v is in scene, my computer froze. If v is in scene, then continue, just don't even bother. If v is destination, return 1, return true, because then we found it in the breadth first search. Otherwise, q dot append left v. And interestingly, we don't need to use any else ifs anywhere because this condition leads it to continue, so we don't have to bother. This condition leads it to return, so we don't have to bother. And we also have it in this order. This is like a slight little optimization because we're going to encounter a lot more situations where v is in scene, where there's only going to be one situation where v is the destination node. So we'd rather have this reached first instead of checking this a million times. The last thing we need to do while we're at it actually is say if source equals destination, return true right off the bat, because this actually won't work if source is equal to destination. Oh, oops, we gotta add this to scene. This is what happens if you didn't have scene. Currently it's not being used without this line. It'll just run in circles forever. So when we run it, I'm curious to see the time complexity, because that actually really interests me in this problem. You can kind of see there's two humps. And initially I thought this would be the fastest approach of the two that I'm thinking of, but I was a little bit surprised to find out that's not the case. It takes the least amount of space because all you have is a queue. No, that's not true. You have the adjacency list, but still, this is a straightforward solution and it will work and it looks good. But next I want to do union find. And union find is a little more advanced and a little more complicated, but once you get used to it, it's a lot simpler. And actually, this is probably going to be easier for me to code than the breadth first search. So instead of using an adjacency list, we're going to use a root and a size array. And the root array is going to be I for I in range n. And the size array is going to be 1 times n. And what these are going to represent, and what this whole sort of algorithm we're about to build represents, is finding out which components are separate, how many components are separate, what they look like. So for example, here there are two separate disjointed components in this entire graph. Here there's just one component. So when we start, we're sort of building these trees in root, and we're saying for each node, what's the root node? What's the node we're choosing to represent that component? So in the beginning, before we parse any of the edges, there's no edges, everything is just its own root. Every node is its own separate component. And if edges was empty, that's what it would give. But then if we, let's say, connect 0 and 1, then 1, its root is 0, or 0's root is 1. We could go either way. And that's where size comes in. Size, if we have a situation like this and we connect them, it doesn't really matter which one. Let's say these all point to 3 and these all point to 0. It doesn't really matter if you have to change all of these 0s to be 3s, or if you have to change all of these 3s to be 0s. But if this had like 10 nodes in this component, it would be way less effort to change all of these 0s to be a 3 than to change all 10 of these 3s to be a 0. And we can do this with two functions. So we're going to define find of A, because that's usually the syntax is A and B. And then we're going to define union of A and B. So find, we're saying, I might point to something, or root at I might be something. There's situations where 3 might point to 4 and 4 might point to 5. And we want to eventually reach 5. So we just kind of walk down the line and say, 3 points to 4, what does 4 point to? Does it point to itself? Because if it doesn't, just keep going. So we just say while root at A is not equal to root at A equals root at A. So it's kind of confusing. And then return root at A. And actually we're doing something here called path compression, where as we go, now after this, if 3 points to 4 and 4 points to 5, at the end of this find call on 3 will point to 5. So the next time, let's say these were connected, this points to 3. When we find 5 from this, we don't have to say 1, 3, 4, 5. We can just say 1, 3, 5, and then this points to 5. So if we had this big chain, if you didn't do this path compression, something points to 2, 2 points to 0, 0 points to 1, points to 3, points to 4, points to 5. That's a lot. That winds up being a different time complexity if we didn't perform this path compression. But that we maybe can talk about that in a minute, but that doesn't really matter. Union, we say A and B are equal to find at A and find at B. And then if size at B is larger, what am I doing? Size at A. Root at A is B. Size at B consumes A and is added, or else we do that the other way around. Okay. And then we don't need to return anything. That's just manipulating these. And then it's pretty simple. We just say for A, B in edges, union A and B. And then all we need to check is source and destination, do they belong to the same component? Which you can just say return find at find source equals find destination. If you said root at source equals root at destination, that would almost always work, unless the edges were arranged in a really unfortunate manner where you still have things pointing and you have to use find on them. Cool. And this one should just work even if source equals destination. We don't need that caveat. I'm a little under the weather. This is interesting. It beats 7%. I was testing this before, and I know that this is very unreliable. But this actually seemed to, on average, be part of this bump, whereas the breadth first search on average was part of this bump. If we take a look, we can see this is a straight breadth first search, whereas this 90% is a union find approach. And, these are pretty unreliable, but I find it's not that unreliable. The variance is certainly there, but if you run these a bunch of times, you'll start to notice the reason why there are these multiple humps for different algorithms. So if we compare these, we compare the union find. The time complexity of this immediately right off the bat is O of n, because we have to make root and size of size n. And the path compression really changes the time complexity here. If we didn't have this, what would happen is root would essentially be mapping out this giant tree, and a bunch of nodes could be pointing to a bunch of things, and everything would eventually point back to 0. That's part of the 0th component, but you have this big tree of stuff where they don't all point directly to 0. But then if you think about it, even with this path compression, where we're setting root at A to equal root at A, it's not quite just O of 1 to have this find. It's slightly above that. And if you didn't have this path compression, it would be log n, where n is the size of each component, but then that's proportional to greater n, so it would just be log of n. But this is actually something different. This is the reverse Ackermann function of n, which is much, much, much smaller than log n. I think it's the smallest possible big O notation you could possibly have before it's just O of 1. So I would think about the reverse Ackermann function as between O of log n and between O of 1. And then because we're doing this for the number of edges, and that's represented by alpha of n, it's going to be m times alpha of n plus n. So slightly more than just a simple O of n. And if we look at the breadth first search, interestingly, let's go back a little bit. Yeah. I mean, this is just straight up O of n. You have the adjacency list, that's m, and then you have Q, where you're iterating through all the nodes in a component, which is a proportion of n. So this is just O of m plus n, which is less. That's a smaller big O notation, but it's so negligible that it's faster to use the worst big O notation, because the size we would have to be dealing with in order for the big O notation to become relevant, the difference there to become relevant, that would be like 2 to the power of 1,000. It would be like more information than there is stored on the Earth. So it turns out the more inefficient big O notation is a little faster because the constants, I guess, are less. And interestingly, I was looking at the very top. This is the last thing I'll say. And this one, maybe I'm missing something, but this seems actually quite inefficient. This person has to iterate through edges for every single step in the breadth first search. And I guess they sort of do a level order traversal, but still this is much less efficient than O of m plus n. But I guess they've figured out a way too to I guess abuse even further the fact that this isn't easy and the fact that n and edges.length are relatively low. So it's kind of interesting and amusing to me that what on paper could be considered the faster algorithms are actually the slower hump here, and then the theoretically slower algorithms are faster, and then the fastest one that they show is in theory the slowest one, at least as it looks to me, but maybe I didn't look at it closely enough. So that's the daily problem.